Welcome back. The next device we want to put into our electric circuits is the capacitor. The capacitor is a way for charge and for energy to be stored in an electric circuit, and this can be done by connecting a voltage to two parallel metal plates separated by some distance. When these plates are connected to a voltage, like a battery shown here, the electrons on one side of the plate are pulled off and moved to the other side of the plate by the battery. On the positive side of the capacitor, plus Q charge is moved to the negative side, leaving it with a charge of negative Q. So the charges need to be balanced. Notice that the plates are not connected. Current is not flowing through the capacitor. Instead, as the charge difference across the plate builds up, this leads to the capacitor storing charge that can then be released and used as a source of energy when needed. Once the voltage across the capacitor is equal to the voltage of the battery, then the electrons stop moving from the positive plate to the negative plate, and you just have this charge separation. Probably the best example of a capacitor is the defibrillator. When someone is having a severe cardiac arrhythmia, one of the things that can happen is that the nerves firing in the heart become completely confused and out of sync. So to try and help out, you can send an electric pulse to the heart and sort of try to reset the rhythm of the heart. So anyhow, the capacitor is charged up, and it takes a bit of time, and then when the capacitor is fully charged, you can release all of that charge in one quick pulse. If you want to use it again, then you will have to wait a while, as the capacitor takes a while to charge up. So yeah, you've probably seen something like that on many medical dramas. You might have noticed that the capacitor looks a lot like the charged parallel plates that generate a uniform electric field that we have spent a good bit of time looking at. And you're right here. This is pretty much the same thing, but now we're looking at how the plates are charged in the first place. So in a capacitor, a very important property of a capacitor is its capacitance. That is a measure of how much charge a capacitor stores when a voltage is placed across the capacitor. The capacitance is defined as the ratio of the charge stored on the capacitor and the voltage placed across the capacitor. The units of capacitance is coulombs per volt, and this is named the farad after Michael Faraday. The amount of charge that a capacitor can store is the voltage across the capacitor times its capacitance. That means the larger the capacitance, the less voltage is required to put a certain amount of charge on the capacitor. The capacitance depends on the size and shape of the conducting plates. So as seen here, the conductance, or the capacitance, is epsilon naught, the permittivity of free space that we've used before, times the area of the capacitor, and divided by the distance between the plates. So in A is the area of the plate, and D is the distance between the plates, and C is the capacitance. This should make sense. The larger the area of the plates, the larger amount of charge you can put on the plate. And the closer the plates are together, the easier it is for the charges to be moved from the positive plate to the negative plate. It's easier to move the charges because the opposite charges attract each other, so the closer the plates are, the easier it is to charge up your plates. Another way of thinking about it is, if you've charged up your plates and they're very close to each other, pulling them away will require work, so it's more stable when the two plates are close together. Notice when we are comparing a resistance and capacitance, a resistance is a measure of how hard it is to move charge through a resistor, so the larger the resistance, the harder it is to push current through the resistor. On the other hand, in the capacitor, the capacitance is how easy it is to move charge across the capacitor. So the larger the capacitance, the easier it is to move the charge. To understand how a capacitor works, we will want to look at two situations. In one case, in the case we're showing here, the capacitor is attached to a battery. That means that the voltage of the capacitor is set by the battery. So in this case, it is 6 volts. And once the capacitor is charged up, its voltage needs to be equal to the voltage of the source it is connected to. So this is what we call a connected capacitor. So in our connected capacitor, that means that the thing that's held constant here is the voltage. So we can mess with the capacitor all we want, but the voltage is set by the battery, so that's sort of pinned in place. The other way we can do this is we can disconnect the capacitor. So in that case, the charge on the capacitor is fixed. So once you've cut the wires, then that means that basically the amount of charge on each plate is fixed. And so then when you move change the size of the plates or the distance, then the charge is fixed and the voltage can change. So in that case, the charge is fixed, and because the battery is no longer connected to the capacitor, there's nothing holding that voltage in place. So you'll have a couple questions about that. Some of those can get a bit tricky in the home. So now if we want to know how much energy is stored on a capacitor, we multiply the charge by the voltage, since that gives us how much work is done. However, the voltage is not constant during the charging process, so it turns out the average voltage is half the final voltage, so the energy stored on a capacitor is 1/2 Q times V. So Q is charge and V is voltage. Since Q is equal to Vc, we can replace Q with Vc and get that the energy stored on a capacitor is 1/2 CV squared. Or if we replace V with Q over C, then we get 1/2 Q squared over C. So this is something that you can keep in mind. If you accidentally touch the side of a capacitor, then you can get a pretty good shock. The amount of energy stored on capacitors can be significant. Alright, so you have some questions to do, and next we're going to start to put capacitors in series and in parallel. Good luck.